Yeah, welcome back. A little bit about these activation functions, wherein what is the input to the activation function? We take a linear combination of a couple of variables with a set of weights and then apply a possibly nonlinear function on it. The output is again a scalar. The input is a vector. We take a inner product with a set of weights, and then after that, activation. So the input is also a scalar to the activation function, which comes from an inner product or a scalar product of the input variables with a set of weights. So the input is a scalar, the output is another scalar. So it's essentially just one variable, one independent variable and one dependent variable. So this is what a sigmoid curve looks like. So this is a practical, this is a counterpart of the unit step function. Unit step function which is either 0 or 1, and depending on, this is the input variable A, and we can orient this slope. So this is the unit step function. The unit step function is pretty interesting. Electrical engineers are well, they swear with unit step functions if you've done a course on signals and systems. But it's interesting. Where do mechanical engineers use unit step functions? Sorry, this is slightly away, but if you know me, the stories seem to interest me more. Where do mechanical engineers look at a unit step function, and where do they design filters like electrical engineers and computer scientists do? So unit step function is it's pothole. Yeah, it's a pothole on the road. And the vehicle suspension is actually a low pass filter. Okay. So what do you want this low pass filter sort of response to be? Do you want a overdamped system? Do you want a critically damped system? Or do you want an underdamped system? It's interesting. You want an overdamped system. Because there are, for instance, there are some vehicles like this, the Suzuki Omni, which apparently has a non-existent suspension altogether. What you feel every little bump on the road. Although my wife says I don't feel much of it because I've got enough natural padding when I'm seated. But the idea is that you want an overdamped system. So any very good vehicle, like most starter vehicles, have got a beautiful suspension. So that's an overdamped system. On the other hand, there are some mechanical systems which you want to be underdamped. Very good example is 16th century pendulum clocks. So that the time period should remain approximately the same even when the amplitude goes down. It's fascinating. Okay, here we use that for a completely different reason. We just want the function to have derivatives of all possible orders. Hyperbolic tangent, that is the counterpart of the signum function, -1 and +1. So this is the original function, signum function, the original function which Frank Rosenblatt used. So this is in fact related to the so this is related to the sigmoid function. Sigmoid is between 0 and 1. What can I do with it? I can stretch it so that it's between 0 and 2. Okay, it's a simple modulation. Now what I can do is I can do a DC shift. I can bring it down halfway. So if I bring it down, I have something between -1 and +1. This is exactly what a hyperbolic tangent function is. Okay, this is identical. What is a rectified linear unit? So this is the ideal diode characteristic. And then a leaky ReLU. So when the x coordinate is 0, don't let the y be 0. Have it with a slight slope. And then this is the one which we had that video of the movie Saudagar, wherein even Dilip Kumar was asking, "Ye ilu kya hai?" Okay. So now let's look at the basic problem of why Frank Rosenblatt was completely discredited by Marvin Minsky, saying that Rosenblatt's perceptron cannot even solve the XOR problem. Today we know that it's a linear classifier, so there's no hope there. But is it possible to tweak perceptron slightly and still get this? So as you remember that I mentioned the tragedy of Rosenblatt's life. at 41 years of age, exactly on his birthday, he passed away in a swimming accident. His boat capsized and he drowned. So, okay, one way is take these and introduce a third variable. Take an AND of all of this, introduce a third variable. So the input feature dimensionality is 2. Introduce a third variable, which is a function of these. Now, philosophically, you might say, well, oh, that's not really nice, because how can I have two independent sources of measurement? I create an artificial third source of measurement, which is based on these two. But it's not so much of a philosophical problem at all. Because if you remember, this is actually this was the trick which, if you remember history, this is something that in the Soviet Union, Vapnik and Chervonenkis had kept hidden from the rest of the world for 30 years. Because Eiserman came about with this basic theory of kernels. He published it in a Soviet Journal of Control in 1964. And in 1992, Isabella Guillaume, Boser, and Vladimir Vapnik had their first paper on the hard margin support vector machine, which actually used the kernel trick. 30 years, 28 years. They kept it in hiding. They used the kernel trick for various problems in defense. And remember 1992, this is 1 year after the Soviet Union broke up. Soviet Union broke up in 1991. Vladimir Vapnik took up a position in the United States. Chervonenkis took up a position in the University College of London. He had a dual affiliation there. So that's when things opened up and the kernel trick sort of came about. Nobody really knew that the kernel trick had been used for many problems in control theory, especially to do with defense, the former Soviet Union. This is basically the kernel trick. Then what is the kernel trick? I've got an input dimensionality. I take this data onto a higher dimension, hoping to find a linear decision boundary. It's something like the example that is traditionally taken is I've got two classes of data which are organized in concentric circles. Sorry, I don't have any slides for that right now. It's like saying that I've got a vada and a donut. Okay, so when I place that vada inside the hole of the donut, there is no linear decision boundary which can separate them. So I can separate them with a knife, but then that knife would be running in a circle. On the other hand, so assuming that the vada and the donut are both two-dimensional entities, now suppose I had a third variable, which is the radius of the vada and the donut. If I take three-dimensional space, then what happens? Because of the larger radius, the vada would float up slightly. It's got a smaller radius, but the donut would float up even more because it's got a bigger radius. So now the vada and the donut can be separated by a sheet of paper along the Z direction. Hopefully that is tissue paper, because both are very greasy things which have absolutely been forbidden by my better half. But that's it. Okay, so that's the kernel trick. Okay, I call it the kernel trick. But when I'm away from my spouse's local receptive fields, I often partake in these sleazy, greasy things. Okay, so with this, one of the things that you note are if I plot these points in three-dimensional space, you'd remember that I had plotted these points in two-dimensional space when I introduced the XOR problem. The XOR problem says that, so I've got a 1 here. So what is the XOR? When exactly one of the inputs is 1. And it will be 0 when they are the same, XNOR essentially, okay? So what is the XOR with three variables? Just an odd number of inputs should be 1. 3 variables, 4 variables, 5, that's the idea. Anyway, with 2 variables, this is what it is. It is 1 here, 0 here. It is perfectly possible to get a decision boundary, but that decision boundary, for instance, would be elliptical. It will not be linear. Now what happens is, so whatever I had on this sheet of paper in 2D, let me put it on the XY plane. So this is the X2, X1, X1, X2 plane. Now what I do is I put this third coordinate along with these. So look at this little animation. So you'll see that this third point, because of which it was completely impervious to the fact that we would have a linear decision boundary, now floats up. Now, because it floats up, you'll note that I can put a sheet of paper or I can put a plane. In between these, I can slide a sheet of paper in between. And that sheet of paper is in two-dimensional space. Okay, although our overall space is a three-dimensional one. So that is embedded in three-dimensional space. Are you familiar with this example of lower dimensional entities being embedded in higher dimensional spaces? It's actually a very good example which I usually like to take. It's like a sheet of paper. A sheet of paper, it's in three-dimensional Euclidean space. Now that sheet of paper, look at its extents along, it's in three-dimensional space. So every point on that sheet of paper has got three coordinates, x1, x2, and x3, or x, y, and z. Now let's look at the spread of that A4 sheet of paper. That spread is more along the length of that paper. It's an A4 sheet after all. Okay? There's a little bit of spread along the breadth. And there's also thickness, which is nearly negligible. So what I've actually told you is, make a guess, it's PCA. It's the KL transform. So effectively, I've got, what is the spread? The spread is the variance term along all of these dimensions, x, y, and z. So the variance along the thickness part is negligible. So that third eigenvalue is very close to zero. Okay, so this is a lower dimensional entity which is embedded in a higher dimensional space. So I don't know, I find these very nice to visualize. Okay, non-mathematical approximate visualization. So this basic idea says that the kernel trick, so my hidden layer in a multi-layer perceptron is actually an implementation of a kernel function. Okay? So this is one interpretation. The fact that you see a slide here with zero contents tells you that I'm completely unprepared. I'll have some scribbles around it. I can get a XOR in another way from basic logic gates. I can handcraft basic logic gates. Okay, why? Because I have a functionally complete set. That is, if I can implement a NOT, if I can implement an AND, if I can implement a OR. Okay, so I've got, or for that matter, if my basic gate is a NOR or an AND, I've got a uniform, I've got a universal thing on the basis of which I can expand it on. So if I have these basic functions, I can create an XOR out of them. Okay, that's another way to do it. But the philosophy would also be the same. Look, this is a two-layer Boolean network. I have either variables which are complemented or uncomplemented. There is an AND layer, and after that there is an OR layer. One hidden layer. So the basic philosophy, whether I interpret this, so this is that ancient Sanskrit lokokti, ekam sad vipra bahudha vadanti. One truth is interpreted by the wise in many ways. So I can either interpret that hidden layer as being a kernel function. I can also interpret that hidden layer as being a sum of products form. This also tells me a third interpretation. The third interpretation is that my hidden layer is actually an embodiment of minterms. So if I've got n Boolean variables, I've got 2 to the power n minterms. So in this interpretation, I'm actually answering, remember that question that I had put, that Sholay question, itne aadmi the. So how many hidden layers should I have and how many neurons should I have in, if I have even one hidden layer? This gives me a constructive way to do it. So if I've got Boolean inputs, I can have 2 to the power n neurons in my hidden layer. So for this separate problem, I can actually have a count of how many I can have. So, but then unfortunately, most things in neural networks, there is an existence proof. That is, there is an, it can be shown that there exists a learning system if it is within the VC bounds. There exists a learning system which can solve this, but there is no constructive algorithm that is going to give me even one of these. So this mostly comes out of experience. And after the 2018 Turing Awards, okay, to Sergey Benjio, then Jeff Hinton, and Jan LeCun, people have sort of been a bit fuzzy about that. They say, okay, if it gives results which haven't been seen before, they're most possibly correct, and these sort of things are fairly acceptable nowadays. There's another example that I'll take up. It's again a handcrafted two-layer neural network, but in this case, the input layer would have 2 neurons. The hidden layer will also have the same number of neurons, and will use the rectified linear unit. So the idea here is that I'll have quite a few of these examples, which are essentially going to do the same thing. Some of them will have a common interpretation out of them, some may not. One little bit of philosophy before I go over to my horribly scribbled sheets of electronic paper. What do I look at in terms of a neural network? We'll also come to the development of deep neural network from a multi-layer perceptron. That is what is today, especially with image processing and computer vision applications. You notice that most neural networks are geared for two-dimensional inputs, because that's how the genesis came about. Jan LeCun's LaNet came about in 1992. It was for images. So those 28 cross 28 MNIST images are all the way to 784 cross 1. Okay, so the number was 784. Sorry, I couldn't mentally calculate it that time. So most neural networks are for those. Nowadays there are 3D CNNs also, which are more natural for three-dimensional inputs. But then whatever they are, so we'll come to things like, where did that part come about from, wherein the initial layers of the neural network, all that they do is they take directional edges. We'll see how that naturally developed. That is, the initial layers of the neural network would do some low-level processing, amongst which directional edges which actually come from the first layer. Then the fact about local receptive fields, how did they come about? That is from where we start off with a multi-layer perceptron. By making some tweaks, we go over to contemporary deep neural networks. Where does this local receptive fields idea come about? Where does the basic idea behind autoencoder-like structure, that is, I have my bottleneck representation being on sort of a nonlinear PCA. How does that come about? There's some very nice developments, but most of these developments are actually more intuitive developments. They're as rough as it can be, but then intuitively they've got a lot of appeal. Then if you look at a little bit of history of deep architectures, look, on a rough scale, there have been only two types of architectures. One of them is the bow tie sort of thing, or a butterfly sort of architecture, wherein the number of outputs is the same as the number of inputs. What is there in between is some sort of a compressed representation of the input space, possibly a nonlinear one. That is one of them. The other is that carrot-like structure, a sort of a reducing structure. Because every other neural network can be represented using this. A GAN is a combination of two. It's got a generator, which essentially has a butterfly or a bow tie-like structure, and the discriminator is essentially a contractive structure like a carrot. You might say that, so if you look at the development of deep structures, if you look at that, look at how AlexNet was a development over LaNet 2012, then how the VGG set of architectures 2014 were a development over AlexNet The thing was that what they showed was that with simpler convolutions, you can actually do slightly better than that. You can actually go deeper. But the problem was that even going deeper, there is a very good reason why there is VGG 16, there is VGG 19, but nothing more than that. That's because of the vanishing gradient problem. Gradient started to vanish. Before that, complete hack from the Google team gave resonates. So have a forward skip connection. Sorry, I'm making too many skip connections in my own lecture. But you'd see that architectures have not changed drastically. And then there have been low cost architectures like mobile net, efficient net. Efficient net was very nice because it also introduced the concept of, well, if I have my complexity limited by this, then what is the best that I can do within these set of resources? So it's a disciplined way to design the power of a neural network. So there's some common thread through all of these. Let me see what I can cover. See, at the end of the day, a neural network is going to be a function of proximity. That is, I have a set of inputs, I have a set of outputs. It's basically, after learning, it approximates a function. Why? It gives a computation. It's important to understand the basic philosophy here, because this gives an architectural connotation of a function. What is a function? The best function is if we know it in closed form. I've got one variable theta, I've got sine theta. It's the most compressed way to represent a function. Closed form. Okay, I know what the function is. I simply put it into this subroutine or macro calculates it. It's the most compressed form of the function. The other way to look at a function is to enumerate all possible inputs and all possible outputs. I can do that for a Boolean variable, although it has got exponential time complexity. I've got n variables, 2 to the power n minterms. Okay, so my truth table would have 2 to the power n rows. And if I want to calculate a Boolean function, I'll need all possible combinations. 2 to the power n choose 0 plus 2 to the power n choose 1, so on and so forth. So the total number of Boolean functions is going to be 2 to the power n, 2 to the power 2 to the power n. Just like for two variables, I've got 16 possible Boolean functions. By the way, have you tried enumerating all 16? You can, including 0 and 1. There are also functions, remember that. So 14 other functions. There's an implication, not x or y. Okay, there's a negative of the, so you can actually give names to all the rest of the 14 and you can still enumerate all of them. So, but see, it's possible to do that exhaustive enumeration for Boolean functions. What if we are looking at a continuous domain and not a discrete domain like Boolean functions? So for this, I can use a table, I can use a lookup table which enumerates whatever inputs I know and the corresponding outputs. So if the input is one of these, then I can straight away do a table lookup and I can give that value of the output as my correct output. What happens if one of my inputs lies, let's say, somewhere between x1 and x2? What I can do is I can assume local linearity. I can assume bilinear interpolation. Let's say this xi is closer to x1 than to x2. So I calculate how much is it closer. I assume that there is linearity. I assume that the outputs will also be in the same ratio. Or let's say if it's somewhere in between, roughly I'll say it's half. I can do something like this. The idea is that for a non-Boolean case, it is not possible to exhaustively enumerate all outputs. And what we want to do is possibly for an unknown value, which was not there in the training set. In the training set in this case is enumeration of all possibilities that I have, that I know. So what I do here is, if I at least should get a quote-unquote reasonable value for the output. This is what a neural network does. This is what neural networks are also good at. So neural network is a function approximator, and just like most of computer science has actually come about from control theory. I think our Drulapati sir here would attest to that. Like this entire thing on, let's say, divide and conquer, then the basic concept of dynamic programming came in from what control theorist Richard Bellman had developed for the US Navy in the 1940s in discrete time control. Okay, he actually called it he called it programming just to give it a attractive name to sell it to the Navy. But the essential ideas had all come from control theory. Then a lot of uncertainty handling in computer science has actually come from control theory. Like the basic idea of neural control. So if I cannot compute a controller for an inverse function, what control theorists, so that is why where traditional control theorists would sort of look at neural control or fuzzy control, saying, that's not really control theory. The idea was to learn a controller wherein it's not possible to get a closed form solution for the inverse function, inverse of the function. So this is where a neural network actually comes, and all of this is actually, a lot of this has come from control theory. And this also tells you that I've run out of these slides. So what I'll do is I'll try to present, I have some of my notes here, and I'll also try to present some of these. So just coming to that basic XOR problem, let me see, I'll show a couple of slides here. Sorry, this is extremely low tech. I'm doing this on the command line. My dirty handwriting. Okay. So, yeah, this is one of the interpretations that I said was that the hidden layer would correspond to a kernel function. So each one of these would be one of the m possible kernel functions here, and then I take possibly nonlinear combinations of, see, these are, so what we are saying is that I'm not taking a linear combination of the input variables, but I'm taking a linear combination of the kernel function being applied on these. This is the idea. So it's not linear in terms of the input variables, it's linear in kernel space. It's not linear in the original X vector space, it is linear in the phi of X space. Okay, wherein phi is possibly a higher dimensional entity as compared to X vector. And if my axes were not X's, but they were phi's. Okay, so this is the idea of one neural network, and the example for this I've already done. Okay, I've already covered here. Now there is another approach for the XOR problem. Look at this. I can handcraft a neural network. So this was the approach number 3 that I talked of. I can handcraft a neural network like this. So with 2 neurons in the input layer, with 2 neurons in the hidden layer, I can actually handcraft this by putting in a set of weights and use a rectified linear unit, okay, and get an XOR function. For instance, here, if I put 1s on all of these, 1 and a -2 here, with a rectified linear unit, the output that I get, I can show that. So these are some dirty computations here, but the output that I get is actually an XOR. Okay, so I can construct an XOR like this as well. All right, I can also have a handcrafted example. Do you remember the part about if I can implement, see, I can implement linearly a NOT gate, linearly I can implement an OR, linearly I can implement an AND. All right. Now if I take a combination of these, so this is perhaps the most natural extension to the perceptron of Rosenblatt, which would sort of answer Marvin Minsky's question. I simply look at x1 XOR x2 as x1 bar and x2 ORed with x1 and x2 bar. Okay, so I can implement these two very basic gates with, for instance, in the last example, we saw a rectified linear unit, a ReLU. Here we take perhaps the oldest activation function around, which is a sigmoid. And here, so for something that is less than minus 4.6 empirically, this is about 0.01, and in this case, something more than plus 4.6. By the way, this is interesting because this is symmetric. This is 0.99. So even these limits are very nice and symmetric. So with this, I can create a NOT gate, I can create an AND gate, I can also create something else, but that will need another slide. Just hold on. Yes. So I can create an XNOR, for instance, from here, which is actually a NOT of a XOR. I can do a lot of this. So the way I like to look at this, there is actually a very nice mathematical proof of this. But this is actually a rather informal and a non-mathematical way of showing that this is a manifestation of a very fundamental notion, that is a feed-forward neural network with one hidden layer can represent any Boolean function. This can be proved in a very nice and formal way. This also gives an intuitive and a non-mathematical perspective of a much more general result, that is a multi-layer feed-forward network with nonlinear activation function. They are universal approximators. That is, they can approximate any function reasonably well. Okay, this is the universal approximation theorem. These can be proved rigorously, but then one gets an intuitive feel if one develops such examples. Okay, now coming to this basic part about where is there the conceptual jump from a multi-layer perceptron to a deep neural network? Or rather, what is a deep neural network? Why does this differ from the 1980s concept of a multi-layer perceptron? So this is the example that Raju told me. This is the MNIST thing wherein these inputs are 28 cross 28 images. So if I linearly lay it out either in raster scan order or what computer scientists call the row major, or for that matter column major order. So this is a 784 cross 1 input vector. These feed onto one hidden layer. At the moment, let's assume just one hidden layer. So if I take all my weights of the neural network and stack them up, how many weights am I going to have? It's going to be a 784 cross 1 vector. Now, let's say I train my neural network for these digits using one hidden layer. Suppose I do that training. And the weights which I have learned, suppose I normalize them and put them into a 28 cross 28 matrix. I look at the numerical values of the weights as if they were a 28 cross 28 image. So the interesting part is that what does this give me? This gives me a way to visualize the weights, not as an ordinary 1D vector, but as a 2D image. This will help us in trying to understand some concepts. So what do we have here? 784 cross 1 input. We have some hidden layers, and I want to classify the 10 digits, which is the aim of the MNIST dataset in the first place. The interesting set is we will visualize them as 28 cross 28 weights. So if one looks at these visualized as images, then what has been empirically found is that these very closely approximate directional edge detectors for images. Okay, they are like detectors for step edges in images. They are different directional step edge detectors. This is interesting. This is an empirical observation. People visualized the weights and found this. And then they saw this to be valid for many general configurations. This is true for deep networks as well. Now we'll come to some other properties of deep networks which actually came about from multi-layer perceptrons. One of them is, well, I've run out of slides here. I'll come to another of my horrible handwriting. Just hold on. Okay. So the fact that we now know that the first few layers would almost invariably correspond to local directional edges, especially for the first layer of connections. For any deep network also, we have mid-level semantic features. Let's say for faces, there would be parts of faces like eyes, nose. And after that, finally, the high-level features towards the end, there'd be higher level things corresponding to different appearances of people. So semantic things would sort of go on. The interesting part about directional derivatives is that in a V1, V2 area of the visual cortex, this is actually what Mother Nature also does for us. Mother Nature over centuries of evolution has designed. So what has come out of this? This is an energy efficient situation so that an organism, based on the nutrition that the organism takes in, that would need to be energy efficient to process, let's say, the visual images that come, let's say, to any mammal. That visual cortex should not expend too much of energy. Okay? So Mother Nature has also oriented real neural networks to be like this, to do these sort of things. Okay, because edge detection as such is not a compute intensive operation. Any other example? Since I see a camera in front of me, see, most cameras have autofocus in them. Do you know what the autofocus heuristic is? In every camera, be it even cell phone cameras, you'll see somewhere in the center of the image, you'll see a small rectangle. The autofocus heuristic is exactly this. So look at the pixels in that small rectangle. So in autofocus, one of the things is you'd hear or you'd see the cell phone camera lens combination going forward and backward. It's a heuristic. It stops at a position where the edge response. How do you calculate an edge response? It's a simple row or a column difference of pixels. Let's say for a 3x3 small neighborhood, it doesn't take up much computational resource at all. It stops wherein the lens combination going forward or backward stops when the edge response is maximum. The difference response is maximum. So this is an energy efficient solution which Mother Nature has also worked on. Okay, this is interesting. Okay, we talked about another way of implementing XOR using minterms. So in this case, if I've got two input variables, it can be shown that with this set of weights, okay, +1 and -1, this also is symmetric, beautifully symmetric. I can have 4 of these, and these 4 exactly correspond to minterms. Okay, so there is another way of implementing the XOR function. So it's exactly this. So the idea is to land up with those minterms in such a way that the function is completely decoded. I have got all 4 minterms corresponding to my 2 Boolean inputs. So 4 neurons in the hidden layer. Okay. I've got a derivation here, but that's okay. Then what else in going from shallow neural networks to deep neural networks? Another thing that people found out while dealing with multi-layer perceptrons for many practical applications, like detecting numerals in the MNIST set, was that if I looked at the weights of all the links which come to a neuron and go out of it, what people found out were actually, it's an empirical observation, most of those weights were zero. The only connections with non-zero weights, significant weights, were from a region which is actually physically close to a neuron. So a neuron in one layer is going to have a set of connections with non-zero weights only corresponding to, let's say, the 3 or 4 closest neurons in the previous layer. So what has happened as a result of the learning? What does this say? This says that I don't need full connectivity between 2 layers. I don't need every neuron of one layer to be connected with every neuron of the previous layer. This is in fact the basic concept behind local receptive fields. In the course of centuries of evolution, this has actually happened in the visual cortex. This has also happened in mammalian brains. So there is only a local connectivity. This says that I don't need global connectivity, only local connectivity suffices. Up till this observation, it was only as a sort of an approximation, what we Delhiites call in the chaste vernacular of the region as jugaad. Physicists used to do that for n-body problems. What is an n-body problem? Wherein if I perturb one particular element in an n-body system, I end up perturbing everything. Rather than that, the approximation which physicists give is that if a perturbation happens, it happens only in a small neighborhood around the ith particle. It's computationally advantageous because I don't have that n to the power n sort of possibilities. It's not a combinatorial problem anymore. So the physicist would need to perform only a couple of local computations and get a sort of solution which would approximate the true solution. So local receptive fields actually ended up from multi-layer perceptrons and empirical observations with multi-layer perceptrons. So this is another way in which deep neural networks differ from multi-layer perceptrons. So deep neural networks would tend to have connections, dense connections only towards the end, so to say, towards the classification part, wherein there will be a very, very small number of layers, what we call fully connected layers, which are typically, why do we need fully connected layers then there? Because we want inputs from all possible neurons, which are actually sort of filtered versions of the information that has come from the full resolution earlier layers, but in the contractive structure, we have had a subsampling. So the effect of all the information in the initial layers, with the initial level of information that is coming in, all of that has been filtered in the contractive structure as we go towards the end, and after that we connect everything, either one fully connected layer or 2 or 3, but a very small number, wherein we'll be able to tackle the complexity in terms of hardware, let's say our GPUs which are there, and then we'll simply go about it. So this is essentially it. Then there is another nice point about electrical engineers learn about convolution, but when an electrical engineer is taught about a deep neural network, the first thing he or she says is, hey, this is not convolution. This is actually correlation. So the term convolutional neural network is actually a misnomer, because in convolution there's that extra step of flipping a signal or an image about the corresponding axes. But then here, since most of the kernel sizes, okay, the signal kernels or the image kernels are actually symmetric. So convolution and correlation actually turn out to be the same thing. But this is actually what convolution or correlation really is, and the fact that it's actually a misnomer. And in fact, one interesting example that is often given for convolutional neural networks is that what is the role of these small 3 cross 3 or 5 cross 5 or 7 cross 7 sort of filters. So most of us would have played this little game in our childhood of what in the Western world is called finding Waldo. So Waldo is this cartoon character with specs and he's wearing a striped t-shirt. So these are find the correct pattern. So these Waldo, there used to be books which used to keep kids busy before digital devices came in, okay, before even television came in, so as to find where Waldo is in all of these. So finding Waldo could be posed as a problem of finding the right convolution kernel, or rather a correlation kernel, which corresponds to Waldo, and moving that all over an image, and then wherever Waldo is present, returning a high response. This is actually one of the very basic things in a deep neural network. In a deep neural network, one important property, we have talked about a couple of properties. First is the fact that empirically, the initial few layers correspond to, if I interpret the input as images, the weights treated as images, they would correspond to directional edge detectors. This is one observation. The second observation is local receptive fields. That is, if I find out the weights after training, it will turn out that most of these connections have a zero weight or a negligible weight. Most of those with significant values of the weights would actually be physically connected to the neighbors in the preceding layer and the successive layer of the neural network. This is the third observation. The third observation is that those non-zero weights are actually going to be common for close-by neurons also. So if one neuron is connected to 4 neurons and has weights of, let's say, 1/4 each, its adjacent neuron in the same layer would also have the same weights. So now do you see how much of compression there can be in a deep neural network? So this is essentially the correlation kernel. This is that finding Waldo problem. So if I have a Waldo detector, my Waldo detector is going to be the same whether I'm applying it to the left corner of an image, the right corner of an image, right bottom, or somewhere in between. Those weights don't change. But even with these approximations, still the number of parameters today in any sample given deep neural network is incredibly large. There are millions and millions of parameters, even with all of these approximations. So just think, this is the reason why multi-layer perceptrons did not quite make the cut. We would have to deal with deep neural networks. So this is, for instance, Jan LeCun's story of trial and error, by which he arrived at the first practical deep neural architecture, which was a bad pun on his own name, LeCun, L-E-C-U-N. So that L-E is also the French for the. So LeNet turned out to be the net. Okay? And Alex Krzyzewski put an even worse pun on LeNet by putting his own name, AlexNet. So LE became ALEX. Google made a further worse pun on the term by having GOOG LeNet. Okay, so that became net. So people have named it in many different ways. So in just a couple of minutes which are left, let me see if I can cover any other fundamental topic. So here I've got things about convolutions, shift invariance. This is that Waldo thing which I described. There's nothing much here. Sorry, I'm not that good a teacher to have everything really well prepared. Okay, so these are some of the characteristics of deep networks. There are local receptive fields, so every neuron is connected to only a fixed number of neurons. Also, the weights are the same. Then, the sparsity is not really that restrictive, because if you look at just this structure, so Y3 here actually gets an input from X5 as well. In fact, this has been one of the most burning questions in 2D neural networks, deep neural networks, that is encoding of neighborhood information. So even the very basic contracted structure of a deep neural network also encodes context, so that I have information about all neurons in a particular layer, but in a more condensed form. But that information is there. But sometimes this is not sufficient. So that spurred the development of recurrent neural networks. Okay, LSTMs, bi-LSTMs, that concept came so that the spatial context. Why spatial context important? Because see, one pixel may match another pixel, but the images would match if the structure around that pixel is also the same as the structure around the pixel in the second image. So that is the spatial context. For one-dimensional signals, the spatial context is the sample values before that and the sample values after that. Okay, what people in signal processing look at in windows. Okay, all windowed filtering, it says that. So basically, people are looking at some sort of a correlation across a window, across a small structure. Okay, then there is that concept of strided convolutions. This is interesting. This says that even with local receptive fields, if I take all possible convolutions, or for that matter correlations, then because I'm doing downsampling in a contracted structure, I'm doing a downsampling, my image size reduces as I go forward along that contractive structure. So the convolutions in between are wasted. Look at that. Now, because I want to avoid that wastage, I can actually put a stride in my convolutions in which I don't consider every one of them. I may skip one of them because anyway, at the next step, I'm going to do a downsampling. So I take only the relevant ones and I put them here. So this is the idea of strided convolutions. Okay, it's a very natural idea. Parameter sharing was something that I talked about in terms of the Waldo detector. And then finally with this, one comes to, okay, Lenet was there, Lenet 5 came about in 1989. 1992, they had their most refined version of the first deep neural network. I guess I have also come to the end of lay time, which was assigned to me, and maybe time for a couple of questions. I'd like to take them. Okay. Okay, so open queue, raised hands. I guess what you can do right now is, Sanodia sir, is there a microphone wherein I can hear, or? No, I can't hear them. So I'll have to switch on my, okay, there'll be a bit of echo. If there is some other speaker which is...
Speak, they will be there. We can hear from the speaker. You can hear, sir.
Okay, can you relay the question in that case? Because either the chat box is sometimes not very natural, but either way, yeah, please. So I've got the chat box up on the screen and
Yeah, so he has some question.
yeah, here it's of course fine, but for online participants. Yeah, please sit and learn. So standing instructions are to sit. In fact, when somebody tells me you're in this standing committee, I say, no, not me. I want to sit. Yeah, please.
Thank you for the beautiful description of the basics. I hope I'm audible.
Yeah, ma'am. Yeah.
I just wish to know your thoughts on relating the compression in a neural network versus this distillation process and teacher-student models.
Oh boy, that is so. I'll just repeat the question. The question is essentially compression in neural networks vis-a-vis other related issue, and what is it in terms of teacher-student learning and how. So I'll go about it. Sorry, I don't have a single slide on it. The first point is actually something which the group at IIIT Sri City has worked extensively on compression in neural networks. So Dr. Sarvani, who also has a talk, she's with ISRO. She had her PhD from this place, and some of her committee members, Tulapati sir was one of them. So people have looked at compression in neural networks in many ways. One of them is filter level, but the first is possibly filter level compression, so that within a layer, if I remove some filters, if I remove some neurons which do not seem to have high weights assigned to them as a part of the learning process, if I have some way of estimating that, then I can take a pair of scissors and I can cut them out from a neural network. So I can do this at a filter level. I can do this at a layer level also. Because for instance, if I find out that during the course of my training, two adjacent layers of a neural network just have corresponding almost just one link having appreciable weights, the rest have weight 0. So effectively that says that most of this layer is essentially extraneous. So I can take a pair of scissors and I can remove this layer altogether. Things start getting a bit more complicated if I want to take a pair of scissors and I want to remove a bunch of neurons from the middle of a neural network. So one of my students has also worked on some of these problems, and Dr. Sarvani also has some publications. We also have got two ways of looking at these. Then there are some other interesting approaches to this as well. One is essentially saying that if I have, let's say I've got automotive applications. So this is one of my students, he's got a BMVC recent paper on this. So he says that in automotive applications, if let's say I'm creating cars and smart cars each with a neural network. Now, if I train all of them to be the same, they're essentially not going to do anything different. Every car is going to be a carbon copy of every other car. On the other hand, I can, because some problems are so tough that some, let's say cars which are going together, if some of them can adaptively learn different interpretations of the same situation, then that complementarity of neural networks, which have the same structure but are exposed to different subsets of inputs so that they would train themselves differently. So that is interneural network learning. I'm basically trying to relate your first question to your second question. There are intraneural network optimizations also, okay, two of which I just described. Then the teacher-student model, nowadays these have come about because this says that if I have a bigger neural network, which has already been trained for a particular activity, I can use its training to train a simpler or a smaller network, which I call a student network. I can use that training. So there are these different models nowadays. Then also are the so-called industry-based models, wherein a smaller model may need to be trained on a particular subset of problems. Okay, so that is another form of distillation. Then there are many other perspectives in federated learning, because this says that now my learning need not be centralized, it can be distributed. I can have some part which is learned differently across. So nowadays people are really playing around with all of these, like saying that if I have got some restriction in terms of compute power, I'm not going to learn the entire thing, I'm going to federate it out and another neural network is going to learn that. So this point actually is a real fascinating point of time now, this couple of years, because people are also looking at collective learning and how to reduce. Let's say the ultimate aim is that to have, let's say, which started with mobile net, having a low cost network which could also be put on something as less powerful, like such as a mobile device, and then go ahead with that. So there are lots of these fascinating approaches. But then again, most of them have come about at the idea level, and there are also proofs of concepts and some basic strategies. But unfortunately, not things are terribly good when it comes to, let's say, something being very having a very sound mathematical basis. Because after all, everything is going to come in a sort of an ensemble. And how do you model that ensemble? Then there are also things like the control theoretic aspects of that. For instance, if I have the same training set, but then if I give it in a different order, would there be stability? Okay, it's for instance things like why suddenly all the multinational companies, even during the 2008 meltdown, why they suddenly wanted to hire control engineers, not computer scientists, not any other ones. That's because things like Google, for instance, in a browser, when you open Gmail, there are some targeted ads that will be based on the sort of mails that you have received, the last 50 mails that you have received. Now, there are stability issues. So if I interchange the order of a couple of those emails, I should get the same targeted ads. So that essential concept of Lyapunov stability also comes in a sort of a non-continuous domain with conceptual variables also. It's also there. So it's really a very fascinating time to look at all of these issues. And unfortunately, since I'm learning this also myself, so I'm not that competent to really answer to.
Thank you.
So we have one more question, sir.
This is online.
Yes, yes.
Can you repeat that question, because I
I
can't
think
hear?
she would ask. Yes, sir.
Yeah, can you please ask Divya Lekha Nayak?
Yes, sir. Yes,
Yeah,
sir. Am I
yeah,
audible?
yeah, I can hear you.
Yeah, sir. Actually, I'm working on image compression algorithms. In an adaptive manner, I'm processing my algorithm, and I found many neural network based concept with the image compression, and I'm very new to the this neural network stuff.
No,
So,
if
can
you
you
have done all
advise
that,
the?
you're much more experienced than I am.
No, no, sir.
I haven't read much of
So
this.
my concern is, I have gone through all the basic. I have studied everything, but the problem is while coming for the implementation part, do you have any key means any tips so that we can implement the codec, whatever we are gonna means like RNN or anything, we can start it from the scratch, or we need to use with the inbuilt functions are available, which is better. Like,
Typically libraries, like most there are these two
so
things in
actually, if
multi.
sorry to interrupt, but if we are going for the MATLAB, it is good, or if it is Python.
Well, we have expert help. Sanodia sir has volunteered to answer this.
Hello?
Sir, please.
Yeah, so no. So from like next session, so I think we have a expert from the Samsung company. So he is going to take all the hands-on session. So he is going
Okay.
to share all the codes, and I'm sure that you would be able to implement all the models, and whatever the doubts you have right now. So he would
Okay.
clear.
Okay,
So
sir.
all
Okay,
the
sir.
4 sessions, so for 5 sessions coming, so he is going to tag.
Yes, sir. Yes, sir. Okay, sir. Thank you, sir.
Thank you.
Thank you.
Sanodia sir, thank you very much for taking the podium. But at a rather rough level, there are there are PyTorch libraries, there are TensorFlow. TensorFlow comes with Google's muscle behind it, and typically what had been observed earlier for different versions of TensorFlow, there was apparently no backward compatibility. So if the library, it used to be a nightmare working across libraries, but nowadays things have stabilized a bit. And there's the PyTorch, there's that other religion, so to say. Huh? What is it? Paradharmo Bhayavaha. So if you follow one of these two religions, shifting to the other one is slightly difficult. But then, yeah, people have normally come across this. And for basic signal compression, the question that Madam had asked here was basically a neural network compression itself. But for basic data or signal compression, the idea is even more severe. It is just that there is some amount of redundancy in the data. That redundancy could be in the spatial domain, that could be in a frequency domain. So if there is redundancy, then I can compress it. That's the idea. And if there is no redundancy, then I cannot compress it. So the best compression, for instance, for an image would be to have the information in one pixel alone. So if the entire image is a constant intensity, I can compress it into 1 pixel alone. But so there are things like there is lossy compression. Lossy compression could be I want to transform the given data into another domain, which is more sparse compared to the original domain. And then I have the inverse transform as well. So that can be lossy, lossless, things like fax. Nowadays, nobody uses fax machines, but fax is essentially run length encoding. It is lossless. After, of course, the resolution loss. And in terms of that is lossless. Then Huffman coding. Huffman coding, I think, whenever I want to teach it, the first thing that I ask students to do is to read up Sherlock Holmes. Are you familiar with the Adventure of the Dancing Men? If you are familiar with that, you actually know the basic idea behind Huffman coding. So Sherlock Holmes in that story is asked to take up a case wherein a certain coded language of a couple of dancing figures was put on the garden. So Sherlock Holmes got a one-to-one correspondence with Oh, I guess Sanodia sir has cut out my network connection. It's 2 o'clock, Sumantra, enough? Keep quiet now.
So we have a